Can you hear me yet, Patrick? All right, I hear you. Good. I was beginning to think I did something wrong here. I know you don't think that's a possibility, but never mind. Okay. So far, you're the only one here so far.
It says Josh is here too.
Josh is. Excellent.
Yeah, I just got in.
Okay, good. Welcome. I'm going to, I don't know if y'all can see when I do this, but I'm scooting Patrick's box up to the top. You may not be able to see that, but you're there. All right, so we got 2 out of 5 here. Hopefully the others will be joining. Let me know if you see or notice anyone else joining, and we'll go from there. First, as far as announcements go, so far all the students seem to have known that. I had 5 students present out of my 10 this morning in Cal 1, and they all seem to know, or they indicated they knew or had a clue on it. But I guess y'all have heard that we will be online for the rest of spring term, right?
Yes.
Okay. There will be no going back to campus this term. So be prepared for this to continue through the duration here. Now, I know that UAB, I believe, and University of Alabama, too, have both basically canceled their spring graduations as well. That's all going to be online or something like that. You will still be graduating, but it just won't be. So I imagine we're going to do the same. I haven't seen anything that indicates that yet. There's a faculty meeting that went on this morning at 11, but I was in my class then. I'll pick it up, and they're either going to rebroadcast it or redo it tonight at 6. So I'll find out then any more information there. So hopefully by Wednesday I'll have some more information to let you know. And we'll figure that out. Any questions, anything, concerns that y'all have, either about how things are going to work or calculus even, that would be a fair question too. Any concerns?
I think last time you said you were going to send us an email with a link to the test.
Oh, you mean test 2?
Test 2, and I didn't get it.
Okay. Now
Blackboard Ultra.
What's that?
It's on Blackboard?
Yeah, it's on Blackboard and it's under message. Same place you got the message about the class today and the code and stuff.
All right. Thanks.
Yeah, and you saw it there, Josh? Is that right? Okay, I think I've lost Josh. I heard him for a moment there, but anyway.
Oh, yeah, I had muted myself because I was talking about parents. I'm sorry. What'd you say?
Okay, I can barely hear you.
Can you hear me now?
Yes. You said you got the test through Blackboard?
Yes, I did. Yeah, I got mine.
Excellent, excellent. Okay, let's talk about that for a moment too. I wish more people were on now so they do know this. And I will include not just your test, but also hint, your research paper, okay? Now, if you do the research paper in Word, you can just send me an email with that Word attachment, and I think you can do it through Blackboard under messaging, and send me your paper send me a message with your paper attached. Either that or email, I don't care which. Now for your test, and half of you have turned in the first test, the other haven't. There's one other person who's not on board yet today who hasn't turned in the first test. You can send those to me, and there's 2 ways you can do that. Number 1, you can scan the test and then send that as an attachment on Blackboard or as an attachment through email. Either one of those. And by the way, I'm checking through the messages. I don't know this new Blackboard Ultra as well. I thought messages was the same as announcement. I found out this morning it's not. So one of my students was having trouble, and I said, well, I sent the last night. Well, no, I didn't receive it. And then another student said, it's through messages. It's not through announcements. I said, aren't they the same? So I felt really dumb, but I'm used to that. But anyway, that's where I'm sending things, and that's where I'm looking. So so if you'll send it either through email or message. And then also the second test, when you finish it, oh, and I said you can either scan it, but if you don't have a scanner, we have a scanner here at the house, but right now the office is so full of, my wife's working in that, I'm up in a bedroom. So it's just pretty congested with all the stuff that we got going on here. We haven't even set up our scanner yet, but you can also take a picture of it with your smartphone. And if you do that, then that's perfectly fine too. You will, I think my computer will receive most of those files. I know some of them used to be JPEGs. I don't know if they still are. You can actually scan, I think, using some of the newer versions of iPhone or smartphones. However you can get it to me, get it to me. And again, either through Blackboard or through email. Okay. So, any other questions? Anyways, any of that kind of stuff? All right. If not, where we left off last time, we had started chapter 13, functions of several variables, and we were in 13.1, which is introduction to functions of several variables, and we were on example 1. And what we're looking at is the domain of these functions of several variables. We had done the A part of example 1, and if you've got your text in front of you, this is on page 873, and top of the page, we had done the A part. We were getting ready to do the B part. And they don't actually show the function here. Let me go back and you can see, here's the B function. It said find the domain of each of these functions. All right, we've already done the A, so let's focus on B. What are the things that would limit the domain of a function in general? What are 2 or 3 things you can never do?
Divide by 0.
Yes, dividing by 0, and number B here has variables in the denominator. Okay, so that's going to be one concern. You don't want that denominator ever to be 0. Okay, anything else?
Negative square root.
Yes.
Or square root of a negative number.
Yes, and we also have a square root, which is also in the denominator, so that cannot be negative. So we can extend that to mean what's inside that square root can neither be negative nor can it be 0. So the thing in the square root has to be positive. Okay, that's going to determine our domain. The other thing that you would normally consider, but we don't in this problem, if you had a logarithm anywhere in the problem. A log, you cannot take the log of 0 or a negative number. So that's both of them. It can't be 0 or negative. So basically what you just told me, I hope you realized, was that 9 minus x squared minus y squared minus z squared. That expression there cannot be negative or 0, so the other way of saying that in math speak is it's greater than 0. Agreed? Not greater than or equal to, greater than 0. Now how could you express that another way? As in moving some things around.
You can move the 9 to the
Okay.
right side.
Okay. And I'm hoping this is what you say. I'm not hearing too well. It's mostly my hearing, but also the transmission. I'm going to add all of these variables to one side and leave the 9 by itself. So that would be adding an x squared, adding a y squared, adding a z squared to both sides. Okay, and these will all add to 0. And I'm going to flip things around if it's okay. And when I flip them, I have to also flip the inequality and say that x squared plus y squared plus z squared is, that's on this side. Notice the inequality is pointing to it, so have it point to that one too, is less than 9. Not less than or equal to, less than 9. For some reason my pen's not writing well. Okay, now, do y'all concur that's what the condition on our domain will be? What does that describe to you? X squared plus y squared plus z squared has to be less than 9. Any images come to mind?
Like a sphere or a circle.
Okay, it's kind of like a circle, only it's three-dimensional.
So a sphere.
A sphere. This is a sphere, and it's the inside of a sphere of what size?
Radius 3.
Radius 3. You're absolutely right. It's not the sphere itself, because it has to be less than that 3 squared, or 9. So it's the inside of that sphere. That's the domain of that function, of the b function. Doesn't matter what the numerator is. That's no concern to us whatsoever. There's no radical there. There's no log there. It's just an x. No problem. It's that denominator. Number one, the denominator can't be 0. Number two, this thing inside the radical can't be negative. Put those two together. That means the thing inside the radical can't be negative or 0, meaning it's got to be positive. And sure enough, that leads to the interior of a sphere of radius 3. So let's see. That was the A part. Here's this one. See, they jumped right to our second or third step there. The x squared plus y squared plus z squared has to be less than 9. Okay, because that was in your denominator there. Consequently, the domain is a set of all points, x, y, and z, lying inside a sphere of radius 3. Oh, and we didn't say centered at the origin. That's because there's no x plus h or minus h, x, y minus k, z minus whatever, l, whatever the next thing would be. That's centered at the origin. We didn't say that part, but that was sort of understood. Any questions on that? Okay, ready to move on. Functions of several variables can be combined in the same way as functions of single variables. For instance, you can form the sum, the difference, the products, and the quotients of two functions of two or more variables. They're going to show two variables here. The sum or difference, f plus g of xy, would be f of xy plus or minus g of xy, just like you would normally do it. The product function would be fg of xy would be f of xy times g of xy, and your quotient function, f divided by g of xy, would be f of xy divided by g of xy, as long as, here's the only thing that you have to mess with, g of xy cannot be 0 now, because now it's in a denominator. So basically, your domain of these combinations, sums, differences, that kind of stuff, are the, and they don't quite say it here, but your domain of the f's and the g's, since that's the one they're using here, you have to maintain those domains. Say if f had a domain, say from -10 to +4, okay, and g had a domain of -5 to 15, then when you did any of these functions, sums, differences, products, or quotients, then you would be limited to those domains that are in common. I think I said -5 to 4. That would be your domain of these, except for that division function. You would then have to also consider where is g of xy 0. And if g of xy turned out to be 0 anywhere between -4 and 5, then you have to exclude that value as well, or those values. So that's They don't go into the domain here, but you do have to keep that in mind as well. So it says you cannot form the composite of two functions of several variables. However, you can form the composite function g of h of x, y, where g is a function of a single variable, not a double variable. H is a function of two variables. Because you see, the h is going, the definition of this would be just like before, g of h of x, y. So that would be g of h of x, y. Well, h of x, y, remember, since it's a function, for any given xy pair, there can only be one h. So therefore, g has to be not a function of two variables, but a function of one alone. So you can form a composition of a single value function with a multiple value variable function. You cannot go the other way. You can't do a multiple variable function composed with a single variable function. Just won't work. The single variable has to be on the outside. So that's the composition of two functions, as long as the outside one is a single variable. Does that make sense? I take that to be yes. Okay, so let's move on. A function can be written as a sum of functions of the form c x to the m, y to the n, where c could be any real number in the world, and m and n, at least for now, okay, m and n, not the rap singer, okay, that are two non-negative integers, okay, non-negative integers. And that's called the polynomial function of two variables. So as long as we're talking about polynomials, m and n can always have to be non-negative integers, okay? There can be functions where those are, negative integers or positive or negative non-integers, but they wouldn't be called the polynomial function. So this is defining a polynomial function in two variables. Here are some examples. Certainly f of xy, if it was x squared plus y squared, we're used to that one. But now we could throw in a minus 2xy plus x plus 2. That's still considered to be a polynomial function because all of your x's and your y's are raised to only whole number powers, okay? Positive integer powers is the other way of saying it. Non-negative integer powers. G of xy, 3xy squared plus x minus 2, perfectly fine. Every one of your variables is raised to a positive integral value. The exponent is a positive integer. These are polynomial functions of two variables. So let's move on. A rational function is a quotient of two polynomial functions. For instance, back here, that would now be, if f was a polynomial function and g was a polynomial function, your quotient function would then be a rational function. When we were saying this, we weren't limiting x, f, and g to being polynomial functions. On this slide, we are. So a rational function is a quotient of two polynomial functions, just like we defined it in single variable calculus, or single variable pre-calculus. Similar terminology is used for functions of more than two variables, three or more. Now, we're probably going to stay pretty much at three variable as our max. It's hard enough to picture what's going on with that. When you get anything more than three, I don't have the mental capability of picturing four or more dimensions. Okay, so try not to go there. All right, that took us through the bottom of page 873. Turning on to 874, the graph of a function of two variables. Okay, this really gets to be fun. A graph of a function f of two variables is a set of all the points x, y, and z, for which z now is that f of xy. So in this setup here, x and y are independent variables, z is dependent on x and y. X and y is the domain, I don't like the way they said that, but the ordered pair, x, y, is the domain of f, okay? So that can be interpreted geometrically as a surface in space, the z is, the f of xy is, a surface in space and the domain of that surface would be the region, generally a rectangular region, okay, that would be kind of underneath that surface, okay? Set of all xy's that fit a certain criteria there, okay? Z then would be your dependent variable, so your ordered triplet x, y, and z would have two independent variables, one dependent variable. In this figure that you see here, note that the graph of z of f of xy is a surface whose projection onto the xy plane is that domain D. Now, there are some places they'll call that R for a region, okay? I'm more used to that. Usually they restrict D to be domain in a single variable calculus. This book uses it also for multiple variable, okay? Now, what do they mean, whose projection? What if you had a very bright single source light shining on that surface from above, way up there, infinite distance up in the Z plane, going up in Z, and shining down on the surface, then the shadow that you see here would be the domain, what's underneath that surface. That's a weird way to think of it, but that's sort of how I think of it sometimes. Okay, any questions so far? Now, to each point xy in D, there has to correspond to a point xyz on that surface, and conversely to each point xyz on the surface, there corresponds a point xy in the domain, D, okay, that region, which I'm used to calling R, okay. So, it almost sounds like that we're almost defining one-to-one functions, because that's almost the same way we describe what a one-to-one function is, okay. For every point is no longer variable value for a variable, but for each individual point xy in the domain, there will be one and only one z on the surface, but also for every point z on the surface, xyz on that surface, there is then only one xy that would correspond to that z value. Okay, so here comes example 2. Consider this function given by f of xy is equal to the square root of 16 minus 4x squared minus y squared. First, find the domain and the range of the function. Now, we talked about domain before. We didn't mention range. Range would be the possible values for your z, which in this case is your f of xy. So if you wanted to, you could write that just to remind yourself. That's going to be, the range is going to talk about that. The domain is going to talk about that ordered pair xy. So, example 1, we basically were already doing domain part, so let's do it here. What would be your restrictions on that domain? Anybody? Are there any restrictions? Earth to class, come in, please.
Hey, sorry, I had a doctor's appointment call me, so I'm back.
Okay.
What's going on?
Okay, what's the domain of that function? Yeah, I noticed you had muted out. Okay. Anybody? What's the domain of that function? Is there any value that that function can't have? What were the...
Well, it can't be negative.
Yeah, the thing inside the radical cannot be negative. So it'd be 16 minus 4x squared minus y squared has to be, I almost said it backwards, greater than or equal to 0. Okay? Where would we proceed from there? Just like we were doing before.
You move the 16 to the right.
Okay? I think I prefer moving the negatives to the right, if that's okay. All right, so let's do add 4x squared, add y squared to both sides. Okay, and that gives me 16 by itself here, because these add to 0, is greater than or equal to 4x squared plus y squared. Okay? All right, now what does that describe for you? I actually, and I think I know why you wanted to move it the other way, I sort of like to have the variables in front too. So if you flip them, you have to flip the inequality as well. That would be 4x squared plus y squared is less than or equal to 16. All right, does that describe anything that looks somewhat familiar to you?
That's a circle with radius 4.
Not quite a circle.
Okay.
Akin to a circle, but not quite a circle.
An ellipse.
An ellipse, you're absolutely right. Now, I don't know if you like the other way of expressing an ellipse or viewing an ellipse. What you could do is divide everything on both sides by 16, and then you would have x squared over 4 plus y squared over 16 is less than or equal to 1. Okay? And then if you wanted to write that slightly differently, it would be x squared over 2 squared plus y squared over 4 squared is less than or equal to 1. Okay? Now, that would be an ellipse with the minor axis of x equal 2 plus or minus 2 and the major axis of y is equal plus or minus 4. Okay? And that's exactly what it would be. So last time when I said quite often these domains are rectangular, not always. Like in this case, definitely not. Okay? So this would be an ellipse including the exterior of the ellipse. That's what the equals part of that says, but the interior and the actual ellipse itself. That would be the domain of this function. Okay? So if I were drawing that, and this requires 3 dimensions, and my three-dimensional drawing leaves very much a lot to be desired. Okay? So this would be x is going, and it's going in the negative direction as well. The z is not going in a negative direction because this is a principal square root here, so that won't be negative. Okay, so if you go plus or minus 2, there's 2 pluses here, minuses there, 1, 2, 3, 4 here, 1, 2, 3, 4 in the minus direction. This would be the ellipse, something like that would be the ellipse that is your domain. It's the interior of that and the ellipse itself. Okay, no breaks in it. Okay, now the question is, what would be the range? So, either this expression here for the domain or this expression here for any one of those 3 expressions can describe the domain. Or actually, this one describes the domain as well. Okay, set of all xy pairs such that I'll write it the simplest way, I think. 4x squared plus y squared is less than or equal to 16. Okay. The pen is not writing well. I don't know why. Okay. So there's your domain. Okay. What about the range? What values can z take on? Any guesses?
Could you repeat the question?
Say it one more time.
Could you repeat the question?
Okay, what values can z take on? We've done the domain, that's this. Now we're looking for range. That is the values for z. What values can z take on given this domain of your function. Okay.
Root 16.
Say that again.
Root 16.
Root 16, which would be 4. Okay. That's the maximum value z could ever have. And when would that happen? X is 0 and y is 0, right? Then you would have that. Now, if you go out to the boundary of that ellipse, that's where the function, you're on this value here, that's where the equal sign holds down here or over here. When you're on that boundary, then the z is 0, because your 4x squared plus y squared is equal to 16. And then the difference between them would be 0 then. So your range then would be the range of z would be the set of all z's such that 0 is less than or equal to z is less than or equal to 4. And because this is the principal square root, we don't ever mess with the negative. So that's why it's always positive. In interval notation, you can't express this in interval notation. Z would be the interval from 0 to 4. It's kind of hard to express an ordered pair. Goodness gracious. Okay. A two-variable ordered pair in terms of intervals. I guess maybe you can find some way to do it, but it's easier to express it this way. All right, and then it says describe the graph of f. How would you do that? So we know this one goes up to 1, 2, 3, 4. That's going to be the maximum value, and it's going to occur there and here. Now, what does that kind of look like to you? Being from Alabama. Second. We talked about it in the very first chapter we did. Number 11.6. I know that was 2 chapters ago. That was a long time. What was that shape called?
An ellipsoid.
Ellipsoid. This is half of an ellipsoid. I was thinking, being from Alabama, I was going to hear half of a football, but that would have been okay too.
I did think of a football.
Okay. All right. You're from Alabama. We'll allow that. Okay. Okay. So yeah, that's about half of a football, which isn't very fun to play with. If you think a football bounce is crazy, just imagine what half a football would do. And then but it's technically half an ellipsoid, the upper half. Okay. Now, let's clear my scratch here and see how they did it. The domain implied by the equation is a set of all points x, y such that 16x squared 16 minus 4x squared minus y squared has to be greater than or equal to 0 because it's underneath the radical. So it has to be greater than or equal to 0. Not in the denominator, so it can be equal to 0. Okay? Then if you manipulate that, you can get it to this form, lying inside or on or inside this ellipse, and that's how we got it. They just magically came up with this, but I showed you how to get it. X squared over 4 plus y squared over 16 is equal to 1. That is the ellipse, and then everything inside that would be the less than part. The range then would be all the values between 0 for z up to square root of 16, like you said, which is 4. 0 is less than or equal to z is less than or equal to 4. That's the range of your function f, just like we said. Okay. Now, I didn't remember the b part. Oh, describe the graph of f. Okay, yeah, we did the b part. A point x, y, z on the graph of f if and only if z is equal to that, and how you could expand that, square both sides. Understanding you may introduce some, what do they call them, extraneous points by squaring both sides. Always that's a fear. But if you square both sides, you get z squared is equal to 16 minus 4x squared minus 4y y squared. And then if you move the variable terms to one side, leaving the 16 where it is, you get that. You add 4x squared and y squared to both sides, you get that. And then you can divide by 16 again if you wanted to, and you get this. And here you see that this would actually be your ellipsoid. That expression right there from 11.6, that was your expression of an ellipsoid. But we know that it's only half of it because you're only allowing z to be positive. Because this thing right here tells you z has to be positive. It's a principal square root, not plus or minus the square root. Principal square root. So that makes it half an ellipsoid. And you know from the graph of f is the upper half of an ellipsoid. And boy, there's, look, well, I guess it's okay, just the perspective of it. It makes it look, this is a more pointed end of the football, and that's a flatter end. That's not the case. But it's the upper half of an ellipsoid as shown here. And then for some reason they showed the trace of the plane z is equal to 2. In other words, take a plane parallel to the xy plane, move it up the z-axis by 2, and that red line is a pretty thick trace of that plane z is equal to 2. All right. No special reason they did that, just to show that's one trace. And then the next, in the book they took it one more step and actually showed the traces of a whole bunch of traces in z, and I really don't care for the ones in x and y, the picture that's in your book, because those aren't really traces. They're sort of like meridia or something like that, which I don't know why they drew it that way. But anyway, that's the traces, which then leads to what we call level curves, and that's probably the reason they did it. This almost seems like a misnomer. If it's level, you wonder how can it be curving? Well, in 3 dimension it can be. Okay. So a second way to visualize a function of two variables is to use a scalar field in which the scalar z is equal to f of xy is assigned to every point, to the point xy. Some scalar z, and it will be a single variable number, z. For any specific point xy, there's only going to be one value, z. A scalar field can be characterized by the level curves, and you can also call these the contour lines along which the value f of xy is constant. Okay? This is a weather map. Okay? Probably a make-believe one, but it certainly could be possibly a true one, showing mostly the U.S., Mexico, and the lower part of Canada, or the 48 contiguous states in the U.S. And these are isobars, okay? Those are lines of equal pressure. You've probably seen these in the newspaper, if anyone's ever seen a newspaper before, or weather station, weather on a commercial station. you'll see graphs that or plots that look sort of like this. What they have done is join every place that they have equal pressure. That's why it's called isobars. Iso means equal. Isosceles triangle, two of the sides are equal. Iso, equal. Okay? Along this curve here, all the barometric pressure readings are 108 millibars, or 1008 millibars. Go out a little way and 1004. Here's a 1008 here with a 1012. So this would be a high pressure area. It's a little bit higher pressure than surrounding. It's not a very strong high, they would say, because the lines aren't real close to each other. They're really spread out. That's going from upper part of Nova Scotia to middle part of the Atlantic states. So that's a huge area for a fairly small change of pressure. Here's another high pressure area, small one, but a bigger one, 1016 up here. So the pressure difference is greater here, and the lines are closer together. Now, what does that mean for you? Usually, if the lines are closer together, when you have a large change in your z for your change of xy really close together, you have a steep gradient. What that means for you in real life is the winds are pretty strong. The winds would be very strong on this side because you have a large pressure gradient going from, well, actually it's not. It's going down to 1,000 and up to 1016. Over here it's 1,000 going up to 12. But still, the lines are close together. There's another high pressure over here. This is a little low pressure area here because it's surrounded by higher pressure. Okay? This is another minor. This is your stronger high. This is a weaker high. This is not as strong as that one, but stronger between these two. That's a high. This is a high pressure area here that's similar to that one, but the lines are closer together, so they'll have more impact. And this is a little low pressure sitting right there. Of course it is. That's close to Seattle. They always are having rain there. Usually low pressure indicates rain. Then there's places down here where there don't seem to be any high or low pressure center. It's just a wave front going through. Okay? So, and just in general, you don't need to know this for this course, around a low pressure area, the winds always rotate counterclockwise, and around in the northern hemisphere, around high pressure areas, they rotate clockwise. Okay? And that gives you information too. Rotating clockwise here brings cold air down from here, brings warmer air up on this side. Okay? Here, same thing. Colder air comes on this side, warmer air moves up here. Colder air moves down here, warmer air moving here. But over here, it's rotating counterclockwise. So warmer air comes down this way, colder air moves down. That's a very weak high. Weak low there, so it's not going to make a huge amount of difference, but this is beside the point here. Just telling you a little bit more about isobars. So therefore, somewhere in here is going to be a front which winds are competing from different directions. This could be bringing warm, moist air up here, cold, dry air down here. You probably are going to have some rain showers somewhere along that front. Okay? Not very strong, but you could have some. But anyway, without those are called your contour lines, which are lines of equal value. In this case, it's barometric values. If you've ever seen a topographic map, and I'm trying to think, Patrick, I think you were in Physical Science 112, right?
Yes, I was.
Yeah, and remember we did the topographic maps. Those are isoclines, areas of equal elevation. You can have isotherms, lines of equal temperatures. Okay, you can just about come up with lines of equal something on just about any. This is a weather map showing the level curves of equal pressure called isobars. Okay. In weather maps on which the level curves represent points of equal temperature, those are, like I was saying, isotherms. Okay. And this would be something pretty common. These look like these are degrees Fahrenheit. This must not be in the summertime because they're only in the 80s down here in Mexico. So this would be a little bit earlier this year, perhaps. 70s here, 60s, 50s, 40s. But here's an area of higher temperature. Now, one of the reasons for this is probably it's mostly over land, and water has a higher specific heat, so therefore it takes more energy to warm that water. But evidently the land is prevalent here. Perhaps you have a low pressure area here that's doing counterclockwise flow that's keeping it about the same temperature. No guarantee of that, but just guessing. Here is an area of colder isotherm at 20 degrees here, and again that's because the land area doesn't change temperature, changes temperature more rapidly than over the water, so this is dropped in temperature there. Okay. But then you have another 20 up there. But this is pretty much north to south. You have similar variations, except for little pockets such as those two, and one down here as well. Okay. Another common use of level curves is representing electrical potential fields, and that type of map, the level curves would be called equipotential lines. You don't have an ISO word for it, just equa or equipotential lines. And those would be measuring potential fields. Usually those are lines of equal voltage. Okay, usually those would be in volts. This one though is isotherms, degrees Fahrenheit. Okay. Contour maps are commonly used to show regions on the Earth's surface, and these are the topographic maps. These would be your isoclines we were talking about, with the level curve representing the height above sea level. And this type of map is called a topographic map, or the lines would be called isoclines. So here is a jagged peak here, standing way higher than anything around it. Okay, that would be right here. They do say, I think they call it the half dome. It looks like you had a fault or something happened and half of the mountain fell downhill. So this is called a half dome, and that would be the region right here, would be this part over here. Okay, and then you go on down, but then after a while you go along the ridge, and the ridge then would represent this part. Okay, on the other side, that part. Now you see some other high peaks back here, and you see you're moving toward those in that direction. There is definitely a valley down here, somewhere right in there, and that would be probably represented by this part here. Okay, and somewhere down here they lost a lake, and that's in a low area as well. My guess, well, I don't know. It doesn't look like from this, well, no, I guess it could. The water going down the way here finds its way into the lake. Okay. All right. So those are isoclines. Okay. A contour map depicts variation in Z with respect to X and Y by the spacing between the level curves. Where those level curves almost look like they're on top of each other, that means very steep slope. That would be, I think they've turned this somewhat, because this seems like this would be this edge right here. Unless it's doing the same thing on the other side, it seems like this would be the edge right there. because that's the steepest slope. The lines are closest together, really, really steep there. It could be that's the backside here doing the same thing. I just can't see the backside to tell. Okay. Much space between level curves indicate that Z is changing slowly, which would mean that would be a flatter area, where very little space indicates a very rapid change of your elevation or your Z, which would be very steep, very, very steep slope. Okay. Furthermore, to produce a good three-dimensional illusion in a contour map, it's important to choose C values that are evenly spaced, and they usually do that. That's called the contour interval. Here's 66 there. Boy, they have them so, they label so few of these, it's hard to, okay. They're only labeling 66 and 86, okay? Well, let's see how many divisions are in between there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 divisions, and you got 2,000 feet, so that would be each one of those dark lines would be 200 apart. Yeah, 200 apart. And then the smaller lines would be, since there's 5 in between, I think that would be about 40-foot contour spacing. I'm doing that off the top of my head. I may be off by a factor somewhere there, but it looks like about 40%. 40 foot, if these are in feet, they may be in meters. They don't indicate that change of elevations. Okay. So the C values are evenly spaced. So here's a hemisphere. That's a pretty easy one to do. F of xy is equal to square root of 64 minus x squared minus y squared. It's called a hemisphere. What would be your sphere that would be represented there? What would be the equation for that? Do a lot of what we just said before. Make this your z, and then you square both sides, lose that, and move your x squareds and y squareds over here. X squared plus y squared plus z squared is equal to 64. So what would be that sphere? Anybody? Is anyone still there? Sphere.
So it'd be
Say again?
64, which is just 8.
Yes, the radius 8. A sphere of radius 8. Okay? And it says sketch the contour map of that surface using level curves corresponding to C equal 0 through 8. So certainly the 0 would be down here on the XY plane. Then there would be 1, 2, 3, 4, 5, 6, 7, and 8. So if you're going to sketch a contour map of that, and this can be in just 2 dimensions, because maps are, your big circle here would be 8, 7 would be, they should be circles, concentric circles, but then as it gets down close to 0, they're closer and closer together, because you see, looking down from above, these look really close together. This one's further and further apart. That's a really poor rendition on my part. Let's see what they show. They show the circle of radius 8 is your C1 circle, and you see this is C equals 7. C sub 9 is that 1 point at 8. C sub 8 is where it's, this is sort of strange. I would have called this C sub 0 down here, but they called it C sub 1, which is fine. They call it C sub 1 is equal to 0. My pen is doing strangely again. That would be the radius 8, and then you can figure out what the others are, but they're not particularly easy to figure out. But the C9 of 8 would be that single point there. That's be 7, 6, 5, 4. They're equal distance apart, but remember you're looking down three-dimensionally, so that sphere is covering the same basically arc length from here to there as you do there to there. It's just that it's falling off more quickly there. The steepness is what matters. Okay, these are the 9 levels of your. Last time it did this, I can't remember if it was the day y'all were here or not. It was because I was losing signal there. Okay. See, oh, there's my cursor. I couldn't see my cursor when that box was there. It said my internet was going weak. The Wi-Fi signal was weak. And I'm upstairs, it's downstairs, but it's just below me. Of course, there is a brick wall in between, but it's usually I get pretty good service up here, but I'm fearful when it starts doing things like that line there. I didn't draw that. I don't draw lines that straight. That was just the pen doing a weird thing. Okay. Any questions on this? How to go from a surface in 3 dimension to a 2-dimensional topographic map, level curves on a 2-dimensional map. Okay. That was example 3. And I forgot to tell you that was the top of page 876. All right. They do more on level curves. No, yeah. Coming up, but they're skipping example 4. So let's back up and do our rendition of example 4. Okay. And also you could go to larsonCalculus.com for an interactive version of this type of an example. And here they give you a hyperbolic paraboloid. Oh joy, I've always wanted to draw one of these. Here it is. Z is equal to y squared minus x squared. And again, my pen is just skipping where it wants to skip and whatever. Okay. Now, that's a hyperbolic paraboloid. How do we know this? Well, I want to cover with my hands. If I was in class, I would. If you cover the minus x squared, that basically is a parabola. Z is equal to y squared in the yz plane. And the parabola is opening upward in the yz plane. 0, 0, of course, is on that, and that would be the vertex, and it opens upward from there. Y can be positive or negative, but z is always positive. That's in the yz plane. So if I were trying to draw that, which I usually avoid like crazy, let me see if I can. This is your x, your y, and your z. This is not the best orientation to do this, but I don't do well with 3 dimension, as you can tell. And this does have negative z's, by the way. Okay, how do we know that? Because when x's are significantly larger than y's, z's going to wind up negative. And they really should go through at the origin here, but we'll just pretend they do. Okay, so if you let x, ignore x, so I have x equals 0. Then in the yz plane, this is a parabola that goes up like this and up like this. Something like that anyway. Okay? Now, that's in the yz plane with x equals 0. Okay? Now, if x is not equal to 0, what you're doing then is, and x would be positive or negative, but what you would be doing would be depressing this, because then the z would now become negative, compared to before. So the next one would be something down here like this, and the same on the other side, and I don't do this well, okay? And then this one would be even further down here. Whoa, that's not what I wanted to do. Something like that over here it would be. So basically, you have your saddle point. If this is your saddle, your legs are going on either side there. Those are going down, but they're parabolically moving upward, okay? Now, if you let the y be 0, okay, now you're in the xz plane. That now is one that's opening downward, okay? So 0, 0 is still a point, and it would be opening like this and like that on the other side. Now, I don't have but you see these vertices here, they're going down, and these are going down. They meet here on this, okay? And this is a terrible, like I said, orientation to do this. It's going to be really hard to tell. But, well, that would be what you have in the xz plane. Now, of course, if you're looking down from the z, when z is equal to 0, that is a hyperbola, okay? Y squared minus z squared, where your major axis would be this way. Well, let's see, it starts here, and well, of course, z would only be 0 at x and y equals 0 too, so that is that point there. But this is an ugly mess, okay? But then as you go up from here, your hyperbole are doing above the x-axis, they're going like this. Above the xy plane, they're doing like this. And below, they're doing like this. And they get further and further down. And that is ugly. It is a terrible mess. Look at the one in the book. I wish they had drawn this one. Why couldn't they have drawn this one? What does this look like as far as level curves? Okay? Where are the values all the same? We know at 0, they're all the same. Okay? 0, 0, 0 is right there. Now, where else are you have that? If you come out x, they're dropping down. Come out y, they're moving up. Negative y, they're moving up. Negative x, they're moving down again. But if these are moving up in y and down in x, there has to be some point here and here, here and here, where they're equal potential or equal value, okay? Because this is a solid figure like you see there, and it's bizarre that it would come out that way, but indeed that's what it comes out being. So let's go to our XY plot, which is what I was trying to draw there, and I can't get my pen to write. There, okay, now it writes 3 times and throws it, okay. So your equipotential lines, your iso whatevers are there, okay, and then you have curves that are going like this here, basically looking like hyperbolas, okay. Okay, and that's what they've drawn on the side over there. As you can tell, I really hate drawing these things, so I'm not going to ask you to draw many of them, but you need to be able to look at these and relate. these, if this is your x-axis, this is the y-axis, which my orientation does not do a good job of doing this. These are plus values here. No, I'm sorry, I said it backwards. I said it the way I drew it. Well, the line I wanted to erase didn't erase. Okay. The pen is just really bizarre right now. Can't get it to do anything. Okay. The x's are the minus and the y's are plus. These are plus. These are minuses. Okay. The hyperboles that open around the x-axis are going down. The ones that are around the y-axis are moving up. Okay. If you had their line, and if you look in the book, you'll see those. They show this is C is equal to 0. I don't know why they chose C. This is C is equal to 0. So this would be plus 2, 4, 6. This would be, oops, I said it backwards. Minus 2, minus 4, minus 6. This would be plus 2, 4, 6, or whatever they happen to be. They did that in the book too. Minus 2, minus 4, plus 2, plus 4, plus 6. Okay. Now I have mine being too sharp up above. You'll see they get actually more shallow. I just didn't draw well. I'm sketching on the run, you might say. Okay. Enough of that. Unless there's questions. Are there questions? I was hoping not. Okay. So let's move on to one example of a function of two variables is used in economics is the Cobb-Douglas production function. This function is used to model as a model to represent the numbers of units producing varying amounts of labor and capital. Producing various numbers of units produced by varying amounts of labor and capital. If X measures the units of labor, Y measures the units of capital, then the number of units produced is the function number of units produced. This is what you're going for. F of X, Y. This would be our Z here. Number of units produced would be some constant C times X raised to the 8th power, the letter 8th power, times Y to the 1 minus 8th power, okay? Where A is some constant between 0 and 1, okay? C could be, seems like just about anything, but it probably does have a cap on it somewhere. Now, you might want to say, wait, why would the units of labor and capital be related in this way? Well, the company only has so much money. If it puts more of its money into labor, then the A is going to be a fairly large number, and of course 1 minus A, and A is between 0 and 1. So if A is fairly large between 0 and 1, that makes 1 minus A pretty small. So you're putting a lot less into your capital, okay? But on the other hand, if you put a small amount into labor, you can afford to spend more on the capital. And I'm assuming when they say capital, they mean capital purchases, like a new equipment that can do things better and faster. Whereas you could have not bought that and then used more labor. You know, so that's the concept here. Kinda, I'm really downplaying it. Okay, so they skipped example 5. Thank you very much. Okay, so let's see if we can find some space to do example 5. This looks like about it. So let me erase all that and do example 5 here. A manufacturer estimates a production function to be f of xy. And again, the pen is doing all kinds of weird things. That should have been an F, parentheses, that should have been xy. is equal to 100, that's the C. Don't know exactly what it stands for, but it's fine, as good as anything. X to the 0.6, remember your A had to be between 0 and 1, and then Y would be 1 minus the 0.6 would be 0.4, which is also between 0 and 1. Those two have to add to be 1. It's the total amount that you have to spend. X is the number of units of labor, Y is the number of units of capital. Compare the production level when X equal 1,000, and Y is equal to 500 with production level for X equal 2,000 and Y is equal to 1,000. Okay. So your function f of, now I did find that if I write more slowly it sometimes works a little better. 1,000 for X, 500 for Y, we're going to compare that with F at 2,000 for X and 1,000 for Y. Now, something that looks like that ought to be somewhat similar. You've doubled both your number of units of capital and your number of units of labor and capital, I said them backwards, but you doubled both of them. So you would kind of expect your production, I don't know, maybe to double. Let's see what we get. This would be 100 times 1,000 to the 0.6 times 500 to the 0.4. Okay, now I'm going to have to, well, I have a calculator here too. Hopefully one of you has a calculator. It may be hard to read my writing because the pen is skipping again like crazy. Okay, let's see what you get. I hope y'all are entering this too. I'm pretty slow with my calculator, so hopefully you'll beat me to an answer here. I'm going to have to turn it aside. I've got my phone. So that's 100 times 1,000 raised to the...
I got an answer.
You do. What do you get?
75,785.
Okay, I'll buy that. Yep. Well, the book got 786, so they just rounded differently.
Well, there's some decimals. It's got 0.828.
Yeah, so they rounded up. Do the same thing with 2,000 and 1,000 and see what you get. The 100 stays the same. Whoops.
Um, 151,572.
151,500. I'll wait till this writes. I swear this is so bizarre. 151,572.
Yes.
And look at that. Exactly, or very close to doubling. Right? So yeah, your production function, if you double your labor and double your units of capital, you should come up with twice the production. And it should make you feel warm and fuzzy that you did. Don't you feel warm and fuzzy now? I hope so. All right. So let's move on to level surfaces. Oh boy. Now what we were doing before, if you had a domain that was a plane, then your range was a surface above that plane. That was two-dimensional independent variables. Your third dimension was your dependent variable. Now we're going to three-dimensional independent variables, x, y, and z, and then your result from that, which I don't know where you will put that, but anyway, that will be your fourth dimension. That will be your answer. So your domain of this would be a level surface. Okay? So as you might guess, depending on what you've got here, this is going back to last chapter, the outermost green thing here is, do you remember what that was called? A hyperbolic, no,
It's
elliptic.
hyperboloid of one sheet.
Yes, that's it. Okay. Then the next one inside that is your cone, right? And then you get to
cone.
yeah, elliptic cone, and then you get to your elliptic hyperboloid of two sheets. Okay, that says you're going from C1 to C2 to C3. I guess these are getting larger in values. Okay, so these are three different level surfaces that you could have to produce whatever actually your C1 and C2 and C3 are your result of that. That's your output. That's your fourth variable. Okay, the result of that function operating on that. So if f is a function of three variables and c is a constant, then the graph of the equation f of x, y, z equals c is a level surface of f. And depending if you, even though it's a constant, vary those c's, and you can go from a level surface of a elliptic paraboloid of one sheet to elliptic cone to elliptic paraboloid of two sheets. Okay. Please, let's not draw too many of these. Okay. So let's first just describe the level surfaces of this thing. What do you think the level surface of that function will be? This would be your, I don't know what you want to call it, maybe W, because that would be the letter before X, Y, and Z. Okay, what would be, they called it C before, but what would be your level surface there? Sort of a hint. Back here, oh, they never gave us a function for that, did they? That would be your function. That would be your hyperboloid, elliptic, hyperboloid, ellipticon, and the 2 and 1. And okay, what does this look like? 4x squared plus y squared plus z squared.
This is the ellipsoid.
An ellipsoid, you're absolutely right. Major axis on the x-axis, no, I'm sorry, I'm saying that backwards. Your two major axes, because you have to divide. Your major axes would be your y and your z axes, and your x-axis would be the shorter one, okay? So these would be circles. Your level surface of your level surface would be circles in the parallel to the YZ planes, and the XY planes and the XZ planes would be ellipses. Okay, so that would be your level surfaces, various ellipsoids, depending on what W you use. Some constant. They called it C before. A small c, and that would be a small ellipsoid. Bigger c would be a bigger one, and so on. So each level surface has an equation of this form. 4x squared plus y squared plus z squared is equal to some constant c. That would be one surface. So the level surfaces are ellipsoids whose cross sections are parallel to the x, whose cross section parallel to the YZ plane, I can't read, are circles, which as I said before, because those have the same coefficients. Okay. As C increases, the radii of the circular cross sections increase according to the square root of C, and of course the X also increases, but at a slower rate. So for example, the level surface corresponding to the value C equals 0, I think we know what that would be. What would that be? C is equal to 0. X, Y, and Z have to be 0. That's the only way you can get a 0 out of squaring an X, multiplied by 4, squaring a Y, and adding that to the square of a Z. Those three, all three would have to be 0. So C equals 0 is real easy. That's the origin, and that's all. Okay? But C is equal to 4. Then you could divide everything by 4, and you'd have x squared plus y squared over 2 plus z squared over 2, 2 squared, sorry, 2 squared. So you would have your y and z axes going out to plus or minus 2, and the x going just plus or minus 1. When C is equal to 16, then you would divide everything by 16, and you would have x squared over 2 squared, which is 4, plus y squared over 4 squared, which is 16, plus z squared over 4 squared, which is 16. Then your circle, your y and z would be going from plus or minus 4, x going plus or minus 2s. Okay. So there's the level surface for C equals 0 is just the origin. For C equal 4, that would be an ellipsoid plus or minus 1 on the x, plus or minus 2 on the y and z. And for C equals 16, an ellipsoid that you have plus or minus 2 on the x, plus or minus 4 on the y and z. So, goodness, what a this really leaves a lot to be desired in my mind. That's exactly how it looks in the book. These are not very good level surfaces. Yeah, there are. If you notice the faint changes in the coloring for X there and there, there's plus or minus 1 there when this is 2 on Y and 2 on Z. Okay, that's the interval. The centermost is just the origin, that's all. And then this one, your X is coming out to here and going back to there, and your Y's and Z's are going 3, 4, 3, 4, 3, 4, 3, 4. So they are there. It's just you cannot see, or I can't see this dimension here at all. All I see is the disk there. And that's not a disk, that's... I think this is a pretty lousy rendition, but anyway, I don't want to draw them any better, so we'll leave those alone. Okay, level surfaces, if the function represented by the temperature at a point x, y, z, then the level surfaces shown in figure 1315, which we'll get to in a second, are called isothermal surfaces. When it was two-dimensional, it was just called isotherms. Now we call them isothermal surfaces. Okay? And I guess that's what that was supposed to be. Okay, yeah. If the function, they didn't say example 6, but this function, if those were, and I can't even picture what would be doing this, But if you had your heat source, I would think in the center, okay, that single point there, and if it's that ambient temperature, then everything's at the same temperature, so you would be there at just a single point at the center. But then as you heat things up, if for some reason you have more conduction in the Y and Z axes and less in the X, then you get a flatter, it kind of looks like a pill that you would take. I'm thinking acetaminophen or ibuprofen or stuff like that. Those little pills, ibuprofen is usually a red pill. That would be kind of shape. The two dimensions are circular, but the third one is much flatter. But then a bigger pill would then be when you had the other. So for some reason you're conducting heat a lot more slowly in the x-axis and rapidly in the y and z. Then they moved to computer graphics. Thank you very much. Okay, I can't do these. I can't even begin to do these, so I'll let you show. The problem of sketching a graph of a surface in space can be simplified by using a computer. Can't everything, mostly. Although there are several types of three-dimensional graphing utilities, most use some form of trace analysis to give the illusion of three dimensions. To use such a graphing utility, you usually need to enter the equation of the surface and the region in the xy plane over which the surface is to be plotted. And you might also need to enter the number of traces to be taken. So if this is your situation, to graph this surface, f of xy is equal to x squared plus y squared times e to the 1 minus x squared minus y squared, you might choose the following bounds for x and y and z. Okay, z being your f. Okay. Number 1, your exponential function is never negative. Okay? So that part's positive. X squared plus y squared, never negative. So you got two positive numbers. X and y could be 0 both, and in that case your z would be 0. So you have to include 0 as a possibility for z. But you can never be negative in z, or your f of xy, because whatever x and y values are greater, that's going to be x squared plus y squared will always be positive, and then the e to the 1 minus x squared minus y squared is going to start at e could be 1 when x and y is 0. I'm sorry, e would be 2.7 blah blah blah. But that's when x and y are both 0, so the whole thing would collapse to 0. Then as your x's and y's get bigger, gradually your x squared plus y squared gets bigger gradually, but your e to the 1, it's going to start getting smaller because it's 1 minus a positive number. Okay, but it's going to, so the first term, which is x squared plus y squared, slowly getting bigger. The second term, starting at e, which is 2.7 something another, and now it's going to be shrinking towards 0. You have an interesting combination there. So you might choose the following bounds for x's, y, and z. The x go from plus or minus, x and y both go from plus or minus, from minus 3 to plus 3. Okay, just to have some values there. Z, if you plug in the 0 for x and y, of course you get 0 for z. Okay. If you plug in the 3 or minus 3, either one, for your x's and y, you will get e to the minus 18, no, 1 minus 18, which would be e to the minus 17, which is an incredibly small number. That's rapidly approaching 0. But your x squared plus y squared, that's going to be 18 times that. So on one hand it's getting bigger, on the other hand smaller. Let's just see what it looks like. My word. Okay. That's all it looks like. Okay. The maximum is reached somewhere in between. This is just going, x and y are both going from minus 3 to 3. Okay. And notice how many lines I have here. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4. They must be doing 5s, because that looks like it's origin. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Yeah. Doesn't look like they're going all the way to plus or minus 3. X's and y. Z, though, is never negative, so everything you see here. At the origin, of course, it's 0, because at the origin, x and y are zeros. Okay? And out here, when you get very large, x's and y's, the exponential part is heading towards 0. It never reaches it, but it's getting awfully close. So that's why you have a flat space there. All the interest is in between 0 and plus or minus 3. Actually looks like possibly even plus or minus 2.5 or something like that. But anyway, that's how you generate. Well, that shows you what it looks like once it's generated. That is, it begins the hidden line routine. It begins by plotting the traces in the foreground. Those correspond to the largest value, x values. Then as each new trace is plotted, the program determines whether all or only part of the next trace is shown. The graphs on the next slide show a variety of surfaces that were plotted on the computer, so we're going to get to that in a minute. If you have access to a computer drawing program, use it to reproduce. I don't, so if you got it, go knock yourself out. So these are different views of the graph of f of x, y is 2 minus y squared plus x squared. Okay? E to the 1 minus x squared minus y squared over 4. Okay, I'm trying to figure out what these three, they're just showing different orientations. Okay, yeah, I thought they were doing different lines or something. Here your xy is sort of what they call an isometric, I think is what they call that orientation. But then they twisted it around not very far, just twisted it a little ways, so this part under the y here is now coming out facing you a little bit more. Part that's dropping off in the back here is also dropping off in the back here. But you don't really notice it. That it's not a big twist. The x's went from here to here, the y's went from there to there. Not a huge twist. But then look at what happens. They twist the y almost all the way around here. So that was a huge twist to there. And the x is twisted from basically here to there. So that was pretty major twist there. And now this dip here in positive y's is up along this axis, and negative y is back here too, whereas the x's sort of were flattening out here and here. They're also flattening out there. So they've turned it around. I don't know why they're showing you this unless you happen to have a graphing device that could do it. If you could, knock yourself out. There's one. Here's another. Traces of this curve, f of xy is minus 4x over x squared plus y squared plus 1. And if you were worried about having variables in the denominator, don't be, because x squared plus y squared plus 1 is never 0. It can't be negative or 0, so don't worry about those. It's good for all values. Notice when x is equal to 0, your trace is 0, so your z is 0. So this is these lines, are all on the, I'm sorry, I said that backwards. Okay, when x is equal to 0, you're on the y-axis, and that line straight through. As you increase x, because that numerator is negative, that's making the value of your function a dip there, okay? Whereas if you decrease your x, you get a maximum back there, okay? But it doesn't hold forever, because of that denominator is going to level things out in the long run, because that's going to dominate over having an x squared in the denominator overpowers the x in the numerator after a while, after it's reached its max, and then starts falling off. So they did traces only in the YZ planes on the first. They did double traces in the XZ planes, XZ and YZ planes on the second. Okay. On the third one, they show the level curves, and this looks like Mr. Magoo or Owl or something like this. Here is, along the x-axis, you get your minimum and your maximum. So for positive x, this is the minimum here, and here's the maximum here. Okay, you can't tell just looking without numbers on it what's going on here, but that is a depression when you're on positive x. It's an elevation on the negative x, and your y is equal to, when x equals 0, you're on the y-axis, so that y-axis is always a value, okay, possible value, and then they extend from there. So there's your another one. That one to me was easier to follow, okay, didn't have as many things. Here we have f of x, y is equal to sine x sine y. So this is a sinusoidal situation, depending on which way you're heading. And just looking at the graphics, the next one, f of x is equal to minus 1 over x, square root of x squared plus y squared. Well, of course, x and y can't simultaneously 0, so this is a open circle down here at the bottom. You cannot have a value there, because you cannot have the denominator being 0. There is no danger of that radical ever being negative, because x squared plus y squared is always positive. So there's that. That looks like a funnel or something like that with a hole in the bottom, okay? And then you kind of act like you're going to flip that over, but not quite. Yeah, because it's not even on the top. What you have in the denominator is an absolute value, so that thing can never be negative. So you're good for all real values x and y, but your 0 for this would be the circle of radius 1, and I can't for the life of me see that circle. It's right around in here somewhere. It seems like they should have drawn a trace for that too, but they didn't. Inside that it's positive, outside that it's negative, because the denominator is always positive. Okay, it's falling off as a square. Pretty exciting stuff, huh? And that also ends 13.1. So homework exercises here. Always look at the concept check. These look a little hairy, that number 3 especially. But I'll let you take a look at that and see, or maybe it's 4. I don't know which. I guess that's 4. But the main ones to work on is either 5 or 7. They both should be at Calc Chat. any of the odds 9 through 19, just checking to see, we go to 2.
Yeah, we're out of time now.
We're out of time. Okay, well, let me
Everyone
just,
else left.
yeah, let me just do this homework exercise 5 or 7, both at Calc Chat. Any of the odds 9 through 19, they're all at Calc Chat, 9's at Calc View. 21 to 31, all at Calc Chat, 23's at Calc View. 33 you can think about doing if you like, it should be at Calc Chat. 35 to 41 should be at Calc Chat, 37's at Calc View. 43 or 45 should both be at Calc Chat. You might try doing as many of 47 to 50 as you can. What you're doing is matching the numbered 47, 48, 49 graphs with the contour lines, which are A, B, C, and D. I think you can probably do all those, but the answers for 47, 49 will be in the back and also, but I'll try to do them all. Any of the odds 51 to 57, and they're at Calc Chat too, the odds are. 51 to 57, they're all at Calc Chat. 51's at Calc View. 59 or 61 should both be at Calc Chat, and you can explore doing 63 or 65. They should be at Calc Chat. I think you could do 67. It should be at Calc Chat, and 69 should be at Calc Chat. Any of the odds 71 to 75 should all be at Calc Chat. 71's at Calc View. 77's a good applied problem at Calc Chat. I would say either 77 or 79. 81 is one of those Douglas Cobb production functions like you did. It should be at Calc Chat and Calc View. 83 is also one of those. So you can do either that or 85 or 87 or 89. They should all be at Calc Chat. And then 91 and 93 are true false. You can try those. They should be at Calc Chat. And we'll begin next time at 13.2. Good deal. Any questions?
No, I don't think so.
All righty. Well, have a good Monday and Tuesday, and we'll see you Wednesday afternoon.
All right, see you then.
All right.
Thank you.
All right. Take care.